All right, so now we're going to move on to this part. This part is a little confusing, but we are going to try to make a average velocity versus T mid graph. That's our plan here. We're going to make a V bar versus T mid graph here. So I'm going to show you how to fill out the chart for the first row, or maybe 2 rows, and then I'll let you guys finish it, and then we'll start graphing. So delta t is just whatever this is. It's actually going to be 1 the entire time, so we can just put in 1. It's literally always like 1 minus 0, and then 2 minus 1, 3 minus 2. The way this lab's set up, it's always the same. Now, delta x is 5 minus 0 here, or 20 minus 5, and then you go all the way down. Now, t mid is just whatever's halfway between here. So in this case, it's 0.5. In this case, it's 1.5. In this case, it would be 2.5. You go all the way down. And then the average velocity is going to be the delta x divided by the 1 there. So you can work that out and go all the way down. So let you guys figure what that would be for all of these. So it shouldn't be too hard. Actually, I'll just do them all now because it's right here. Oh, this one is 35. If you're confused, you should definitely pause the video and do it on your own. I don't mean to take this away from you. All right, so I have that. I'm going to graph that at this point now. Just figure out how you want to scale everything. It's going to be a little different for everyone, but it shouldn't be too different from before. So I'll let you guys do. All right, so I made my graph. I went every 4 boxes a second, and the reason I did that is that you're always plotting on the midpoint, so that's how I did it. What you should see here, this relationship, this is linear. I don't think I mentioned it before. This like curve you see here, so the curve on like a position time graph, and I'll redraw like a tiny one because this one has a lot of work on it. So this is exponential, or you can say it's like quadratic. If you imagine like a y equals x squared formula equation, you would imagine like a quadratic that looks like that. So on like in algebra, I'm sure you've seen that. So this is an x squared equation starting at time of 0. That's what this looks like. All right, and going back here, we have this linear relationship now. Before we talk about why we see this, I want you to make one more graph, and it's this one based off these points. All we're going to do is we're going to take this time and we're literally squaring it. So sometimes we mess with data like this and they ask you, hey, square the time. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36. All right, we've squared it. Now we're going to plot t squared, whose units are seconds squared, versus x, which is centimeters. So let's plot that and then come back to me. All right, so after graphing my x versus time squared graph, this is what I get. And notice this is also linear. So comparing this to the very first graph, my position time graph, I had this quadratic one. Then I have this V average versus T mid. And then I have this x versus t squared. And so these two are linear. The first one was quadratic. So why is that happening? All right, let's go down to these questions and see what they want. So they want us to know what the significance of our velocity time graph slope is. Well, let me solve what it is. So this data, rise over run. If I'm going to make an equation for this, it's going to be v is equal to m times t mid plus my initial v naught. Now, I'll say, v naught, normally we have to solve it. I'm going to assume it's 0, and just for simplicity, we'll assume it's 0. V is equal to, my slope is going to be rise over run, so it's going to be my last point compared to my first point, and my last time versus my first time. So 55 minus 5 over 5.5 minus 0.5, or 50 over 5, or 10. And my units, so my units for V are centimeters per second. And my units for time are seconds. So just to be clear, let me put my units down. To be clear, this second and this second will not cancel each other out. It's almost like I'm writing it like this. This is the same way I'm writing it of centimeters per second times 1 over second, where 1 is just, like this is a fraction second basically. And what that means for my units is I'm getting this 10 centimeters per second squared. So, okay, those are my units there. We can try to parse out what that means, and maybe we should parse out what that means. What I'm reading here is that my slope is saying, and I'll go back one more because this is a very important concept. I have a slope here, and I know that slope is velocity, and velocity is how much your position, your y-axis, changes versus your x. So if I apply the exact same logic here, I can say, oh, this number is how my velocity is changing over time. And I'm getting 10 centimeters per second squared. How accurate is that? Well, let me compare it to this. So I'm going to look at my data. For every second that passes, how much does my velocity increase by? So 1 second, 10. 1 second, I increase by 10 centimeters per second again. And if I keep following this logic down, that seems to be the case. By the end, and by the end I mean 5.5 seconds, I'm at 55 centimeters per second. All right, so my slope, so the significance of my slope is the rate of change of my velocity to time. And for every second that passes, my wheel is increasing a speed of 10 centimeters per second. All right, so that's a pretty big concept. Now let's do the next graph, position versus time squared graph. So I'm going to do the same thing, rise over run. These units will be interesting. So I've got 180 minus, and I think we start at 0. Yeah, 0 over 36 minus 0. And I'm going to get a slope here of 180 over 36, which is 30 over 6, which will be 5 centimeters per second squared. Yeah, let's talk about those units too. So remember the x is centimeters, and then t squared is second squared. So this is more straightforward of what my units are, centimeters per second squared. If I wrote out this formula, this is what I would get. So x is equal to m. Now, x is my vertical axis. My x-axis is whatever's there, which is t squared. And then plus x naught, which is going to be 0 meters. And they actually gave us that data. So what my m is 5. So x is equal to 5 centimeters per second squared times t squared. All right, so there's a lot to unpack here. This is a very weird equation to get. It looks like it almost shouldn't be quadratic, right? So we're getting this x is equal to something t squared. But what if, I go back to my position time graph. I never made an equation for this, but I think if I imagine like this is y equals x squared, that looks actually very similar to what I'm getting down here with this equation. So what happened here, I did this process which is called linearization. So zooming back in, big picture, what is this class about? This class is about taking complex concepts and trying to make it orderly, trying to make it so our mind works with them. We were given a very intimidating graph, I would say, definitely the most intimidating graph we've had to interpret so far, this curvy graph. I found out that, hey, what if I squared all of the t values? And what happens is basically they all start moving towards some sort of slope here. And we form a slope out of it, a straight line slope, I should say. And we get a linear graph. But we can't just say, this is x versus t anymore because we squared all the t. So that's where we got the value from. So we have this x is equal to 5 centimeters per second squared times t squared. So what I want us to note is that I got 10 centimeters per second squared on this graph, and I got 5 over here. So the question is, those two numbers are related to each other, and I think we can find out how to get to that number. If we think about like this versus this is double of this. And if I had different data sets and I tried to do this experiment again, maybe I get 20 here, but I would end up getting 10 centimeters per second squared then. So whenever I do this linearization, what ends up happening is, this is one value and this is a value that's half the size if I'm trying to do like a position versus time squared linearized graph. I'm gonna pause the video here and let you think about why that is the case, why the numbers are ending up that. I went ahead and put the equations for 17 and 18 there just for us to view right now. So I have this number 17 graph, this slope here, and this is telling me the rate of change of velocity, and this looks like the exact same information. Now this is important to note. Because we've manipulated the data here, we have to add something to fix what we understand about this. And this is where I'm going to introduce the theme of this unit, acceleration. All right, what acceleration is the rate of change of velocity over time. And I'll actually give a definition for velocity again down here just so we can compare it. Velocity is the rate of change of position. And actually, I'm not even going to include over time. Whenever you see rate of change, that means per time. So if I say rate of change of position is delta x over t, acceleration is delta v over t. Now, I guess the big question I have for you is, which one of these is actually your acceleration? Which one do you think it is? And I've kind of given you the formula here. The formula for it is delta v over t. And so if I think about what my graphs are actually calculating, this is the only one that actually is delta v over t. This one right here. This is delta v over t, the way I got that 10 centimeters per second squared. So my acceleration for this whole wheel lab is 10 centimeters per second squared. Now, that's neat and all. Why am I getting 5 centimeters per second squared? That is an acceleration unit. Notice that acceleration uses centimeters per second squared as units. So why am I getting that value here in my x graph? And basically, two things. First off, this actually doesn't tell you velocity, it tells you your position. So it'll accurately tell you your position. However, if you want to know what your acceleration is and you only have a linearized graph, your acceleration will be 2 times whatever your slope is from your x versus t graph, from an x versus t squared graph. So that's something to note. Linearization, I can use that. I can now interpret the world in a simpler way, a linear way, but I have to understand that there are some limitations to it. And one of them is that I have to assume that the acceleration is only half as much as I found there. So anyways, the acceleration in a x versus t squared graph, you have to double it in order to get the right amount. So, all right, high level concepts, we'll continue this in another work.